Hi, my name is Jacob Nelson, and in this presentation, I'm going to be walking through a technique that we developed to support linearizable range queries for linked data structures. This work was done in conjunction with Ahmed Hassan and Roberto Palmieri, and we're part of the Scalable Systems and Software Research Group at Lehigh University. The challenge that we set out to address was how to provide linearizable range queries for linked data structures. Linearizability is a well-known correctness criteria in which a projection of the set of concurrent operations of an object is mapped onto a serial history, and that mapping satisfies two constraints. First, operations all have to appear to take effect at a single point between their invocation and return, or the linearization point, and all operations must respect real-time order. Now, for range queries, this is particularly interesting because unlike point operations, a range query could be long running. It may access many elements. So the collection of the result set of a range query has to be equivalent to a serial execution of the individual gets composing it without any interleaving of updates. So the question we sought to answer was, how do we provide this linearizable operation without sacrificing performance? Now, existing solutions can kind of be bucketed into one of four strategies. First, we can stop everything and only have a single operation be performed at a time. And a global lock will get the job done, but performance is kind of bad. Another option is to observe that an inconsistent state arises from concurrent writers. So for example, RCU and RLU, if you're familiar, are techniques that allow writers to wait for readers to finish. And thus a reader sees the current state of the object or data structure, in this case, as the snapshot it'll use to generate its result set. Another technique that's interesting is what we call a fix-up technique. So for example, a recent epoch-based memory reclamation technique, range query technique uses this in order to allow a range query to determine what nodes it might have missed during its traversal. So basically, we're going to cache some state. We're going to maintain this state in case we need it later on. Now, the approach that we take is an incremental approach. So we're going to build up our snapshot over time and allow a range query to observe a consistent view at each individual update. And to do so, we're going to use a variation on versioning to build versioned pointers. Which brings me to kind of the first part of this talk, which is the basics of bundling. I want to describe what it is at its core. And that is a building block for linearizable range queries. So we have a bundled reference, which encapsulates the idea of versioned pointers. And by using a version pointer, a range query can just follow the reference that corresponds to its consistent snapshot. To do so, we're going to have a global timestamp with which we're going to label new edges that are added by updates with the version corresponding to that update. And we're going to allow range queries to read the global timestamp and proceed using it to generate a snapshot of the data structure at a particular point in time. This allows us to have incremental snapshots. Each update adds a new edge with a version, and the range queries can traverse these versions. Importantly, this allows a range query to traverse only those nodes that belong to its consistent snapshot, as opposed to possibly additional nodes. I also want to highlight that our technique augments the links in a data structure as opposed to replacing them with version pointers. And this enables for high performance optimistic traversals, a technique that we'll get into a little later. So in order to make this more concrete, I want to walk through a simple example of a linked list and talk about how these bundled references are maintained. So first, we're going to take an empty list with a head and a tail that are our sentinel nodes, and we're going to insert a node with a key of 20. At this point, instead of replacing the original link as we would do in a normal linked list algorithm, we're going to add a new entry into our bundle that represents the newest version of that particular link. And so by following the version at this particular point in time, global timestamp of 1, we can see the data structure as it exists. Now, if we do the same for key of 30 and 10, we can see that at each point, we're adding new entries into these bundles and labeling them with the corresponding timestamps. And thus, it allows us to have a view of the data structure at a particular point in time. Now, if we want to delete 20, we're going to, again, add a new entry into the bundle that points from 10 to 30. And we will keep the old node 20 around until we can be sure that no other operation is going to need it. So at this point, if we have a range query come along, we can have it read a global timestamp before and traverse the data structure corresponding to its linearization point. Now, if the range query happened to have read a global timestamp of 3 before the deletion took place, then it's going to wait until the deletion completes and observe that that edge is newer than its linearization point and see a consistent view. So with that in mind, we can now talk about how we apply this technique specifically. And this is through a process that we call bundling. So bundling is just a process of adding bundled references to a linked data structure in order to support linearizable range queries, which is our goal. It's based on the idea of a bundled reference, or a bundle, which is our version pointer. It's just a list of pointers with their versions that allows us to dereference the value at a specific point in time. We apply this to a lazy list, an optimistic skip list, and a citrus binary search tree. But in this talk, I'm going to limit the discussion to just the lazy linked list. Now, on the right, you can see the API of our bundled references. The first two calls are related to updates, and the last call is related to traversing the bundles, specifically making a traversal that's consistent with a given point in time. So prepare bundle is going to introduce add a pending bundle entry to our bundle that references the value pointer. This allows us to signal to any readers that may observe it that an ongoing change is taking place, and they will wait until this is finalized. Finalizing a bundle means applying the timestamp corresponding to the update to that particular pointer in the bundle. And this allows readers to actually use the version pointer corresponding to the update in its traversal. Now, when we want to traverse the data structure, we're going to use this called dereference bundle, which is going to, given a timestamp, find the maximum version in the bundle that is less than or equal to our timestamp. And I'll note again, we're going to wait until any pending entries are finalized before we proceed. And this enables our readers to traverse the data structure consistently as it existed in a given moment in time. Now, I would like to point out that this process isn't necessarily automatic. It requires that we make small changes to operations in the original algorithm to support this bundle maintenance. And it also allows us to selectively do this. For example, in our skip list, we only augment the bottom data layer of the skip list as opposed to the index layer as well. It also requires that we reason about the baseline data structure in terms of correctness. So for example, our inserted nodes need to be protected until our bundles are completely finalized. And this is so that we can ensure nothing goes wrong while we're inserting a new node. So for example, in all of our data structures, they follow a two-phase locking approach, making this relatively straightforward. The last thing I want to note is that the implementation of the bundles themselves is orthogonal to the approach. In our implementation, we use a sorted linked list of entries, but this is by no means a requirement. Okay, so we have a general intuition of how bundling works. We're maintaining version pointers. We're using a global timestamp to label them. But I really want to dig into the details of our lazy linked list to give an idea of what it takes to actually apply this technique to a data structure. First, I want to point out the changes that we have to make. We have to make changes to the update operations and the get and range query operations. Well, we introduced the range query operations. In terms of the updates, we're going to insert bundle entries whenever we need to. And in terms of the read operations, we're going to use those bundle entries in the traversal. And we'll talk a little bit more about this later. But note that we can actually use the existing links as well when we need to. Which brings us to a discussion about how we change the data structure. The primary change really is in the node itself. And so here our list is going to be augmented with this bundle. And we importantly do not replace the next pointer because we'll leverage that for an optimistic traversal later on. Bundle maintenance is sort of the critical part of an update. Whenever we get to the point where we want to insert a new node, we have to make sure that the bundles represent the newest version of our list. And so to do so, anytime we insert or delete a node, we're going to perform these 4 steps. We're going to first insert a pending entry to notify any ongoing readers that a change is happening. We're going to increment the global timestamp to set the linearization point. And then we're going to execute the original linearization point, for example, swinging the pointer or setting the marked bit. And then we're going to finalize our pending bundle entries with the timestamp that we incremented in step 2. So more specifically for an insert of a node, this is the process that we'll take. We're going to traverse to the insertion point as usual. We're going to lock the predecessor and the current node, and then we're going to insert a new node initialized to point to cur and the pending bundle entries in both prev and new. Next, we're going to increment the global timestamp, and then we're going to finalize our bundles, we're going to swing the pointer from prev, the next pointer from prev to new, thereby setting the active path. And then we'll finalize our bundles with the global timestamp and release the locks, and then we're done. For an insert, this process is very similar, right? We're going to traverse to the deletion point. We're going to then lock and validate that our nodes are still in the data structure. And then we're going to prepare the bundles. And we're actually going to prepare bundles for both the previous node and the current node that we're deleting. And we'll talk a little bit about why this is later. We're then going to increment the global timestamp, set the marked bit, swing the pointer, and then finalize our bundle entries with the new global timestamp and release the locks. So at this point, we have all of our bundle entries corresponding to the updates that we've made. And now we can allow a range query to traverse the data structure and see a consistent view. So we're going to begin with a naive algorithm so that we can get the idea of how this works, and then we'll introduce our optimistic traversals. So this naive algorithm consists of 3 steps. Really, we're going to set our linearization point by reading the global timestamp. Then we're going to traverse the data structure using our dereference bundle call. And then once we get to the range, we'll collect the result set and return to the caller. So to illustrate this, I want to walk through a simple example of a range query being performed with a concurrent delete. Now, let's assume that the range query started, it read the global timestamp, and then it was descheduled. And now a deletion comes along and performs all of the steps up to the point where it would finalize the bundle entries and release the locks. At this point, our range query is going to become active, traverse to node 10, and now it has to make a decision. It knows that there is a pending entry in the bundle of 10, but it doesn't know the value at which it's going to be set. And so it has to wait until the deletion becomes active, finalizes that edge, and finishes before it's able to make its decision, at which point it's going to notice that the edge labeled with 4 isn't consistent with its linearization point, and thus will take the correct path through the data structure. Now, in terms of optimistic traversals, we want to try to improve the performance of our technique, specifically when we don't need to use the bundled references. And this all hinges on the observation that our bundled references have non-negligible overhead when we dereference them, meaning we have to look through the list to determine which version of pointer to use. And so what we do is we break a range query into 3 particular phases. The first phase is the pre-range phase, during which we're going to traverse our data structure without using our bundled references, using this next pointer. This allows us to avoid the cost of bundled dereference. Once we've reached the node immediately preceding our range, we're going to read the global timestamp, and we're going to transition to using the bundled references. Now, this is critical that we stop before our range starts so that we traverse into the range using a consistent view so that we don't miss accidentally any updates that might have happened concurrently, but still before our linearization point. Now, once we've reached the range, we can traverse the range using our timestamp and the bundled references to collect the result set. I also want to point out here that we actually have to treat our get or contains operations in the same way, except we just have a range query of a single element effectively. And this is necessary so that we can ensure a consistent linearization point of our range queries and our contains. Now, I mentioned earlier that we're going to also be inserting a pending entry into our deleted nodes. And without going into too much detail here, I just kind of want to give the intuition why. Now, if we're traversing part of the data structure without our bundled references, then it's possible that we end up at a point that has been disconnected from the current state of the data structure. But by inserting a pending entry in our deleted node back to the head of the data structure, we can effectively revert back to our original naive algorithm and traverse the entire thing using our bundled references. However, in our experimentations, this happens rarely. So this technique is applicable to more than just linked lists, right? So in our paper, we talk about bundling and optimistic skip lists. And again, this portion is kind of just a teaser to hopefully get you interested. And I'll refer the audience to our paper for more details on these particular data structures, but you can kind of get the gist. Here, we leverage the fact that we don't necessarily have to keep a bundled reference per link in the data structure. We can actually save space by just doing it on the data level. And so a range query from, say, node 15 to the end of the list with a timestamp of t+1, where the node 25 was inserted before the node 22, gives us a traversal of the green path here. So we're going to use the index layer up until our start of our traversal, and then of our range, and then we're going to traverse our range using the bundled references. Here, I'm only showing the transformation of our citrus binary search tree when we delete a node, but this concept is similar. Anytime that we're updating the data structure, we're going to maintain the history of links, allowing a traversal of the data structure to be to see a consistent state at a particular moment in time. Now, one thing that I haven't talked about up to this point that I'll also refer to the paper for is how we deal with memory reclamation. Under the hood, we're using epoch-based memory reclamation to identify when we can reclaim nodes, and we use a background process in order to clean up bundle entries that we don't need. So in our evaluation, we're actually integrating this memory reclamation, all the facilities needed to track which bundle entries are stale. We're just avoiding to actually walk through and clean up the stale entries, but we are freeing all of the necessary nodes. In our evaluation, we compare ourselves to three important works. The first we call EBR-RQ, which is a recent technique based off of epoch-based memory reclamation, in which updates are going to label nodes with their insertion and deletion timestamps, and a range query is going to walk the data structure, collecting its result set, and then it's going to scan the limbo lists in order to finalize that result set. So we can classify this particular strategy as a fix-up strategy. RLU, on the other hand, is going to block the writers until the readers are done. So a write is going to log its writes and wait until readers that might see a value to be overwritten no longer need that version. Readers are announcing themselves as they start, and then either accessing the original value or this log value, depending on the situation. Now, writes are synchronized with each other using some other means, for example, fine-grained locking of the original algorithm. The last thing we compare ourselves to is a concept called vcast, which is a wait-free implementation of a versioned cast object. Now, this was originally designed for lock-free data structures and has a lot of similarities to bundling, and we can actually adapt it to the lock-based world. So effectively, what we're doing is we're replacing the linearizing writes with a version cast. And so this allows us to see a consistent view. But one distinction I'll note is that vcast actually replaces all of these links and linearizing writes, whereas we're able to just augment them. And we'll see the impact of that in the optimistic traversals. So just to kind of give a comprehensive view of the competitors we're including, we're looking at unsafe, which doesn't include any instrumentation for our range queries, but all other operations are linearizable. We have the three competitors that I talked about on the last slide. And then we also have two versions of our own approach. The first is what I've described up to this point. And the second one is the same technique, but allowing the range queries to be responsible for driving the timestamp. And this was a way to look at the impact of the responsibility of timestamp driving. In our experiment, we're using a machine that has 4 processors, 192 hardware threads, and a relatively big cache. In our experiments, we're going to have a given mix of updates, contains operations, and range queries given as percentages. And we're going to have our updates be evenly split between inserts and deletes in order to maintain size stability. And then we're going to vary the number of threads from 1 to 92 in most cases, and we're going to fill each NUMA zone before moving on to the next. Now, all of our range queries, unless noted otherwise, are going to be of length 50 in these experiments, and the data structure sizes are for our linked list 10,000 and our skip list and citrus tree 1 million elements. So let's look at a read-only workload. I think this is illustrative of the performance of our range queries kind of in isolation without the impact of concurrent updates. And the first thing I want to point out is that compared to VCAS and EBR-RQ, we're able to win because of our optimistic traversals and our optimal range collection. We avoid the dereference overhead when we don't need it. And we also are able to only visit those nodes that are required by our particular snapshot. Whereas for EBR-RQ, that might not be the case. However, in contrast to RLU, which is much better performance in terms of the read-only workload, our technique has the overhead of bundle maintenance and dereferences, in this particular case, dereferences. And so we aren't able to capture the full performance of unsafe. Okay, so I just want to take a step back and talk about what were the actual data structures that we're seeing here. And this is going to be the same set of data structures we'll see in the next couple slides as well. So on the left, we have our skip list, and on the right, our citrus tree. We're varying the number of threads, and we're looking at the throughput. So again, really here, we're just seeing that our optimistic traversals and our incremental approach pay off. Now, if we transition to a read mostly workload where we introduce 10% writes, but still have majority of reads, we start to see some interesting things happen with some of the other techniques. We still get good performance because of our optimistic traversals and our incremental approach. And now we see that RLU in the presence of updates is actually suffering an unfortunate amount because it has to synchronize with our range queries and our reads. Now, on the other hand, we're able to capture the fine-grained synchronization of the underlying data structure and also leverage the incremental snapshots to balance performance of both range queries and reads and updates as well. I will point out that at this point, we start to see a little bit better performance of VCAS compared to our technique. And this is primarily because we are blocking our readers whenever a pending entry is inserted, which becomes even more obvious when we look at a write-heavy workload. So in this case, for the skip list, performance is roughly equivalent across the board, but for the citrus tree, we start to see a little bit of disparity between them. And specifically, we see that VCAS outperforms our approach mainly because of this application of a lock-free setting of the values, whereas we're blocking. But compared to RLU and EBR-RQ, we get better performance because we're, again, capturing this fine-grained synchronization and taking advantage of our incremental snapshots. Now, the last thing that I want to touch on is the behavior of our optimistic traversals. And to do so, we're going to look at our linked list specifically. This is because the performance of a linked list is dominated by the performance of its traversals. So we can see here that the optimistic traversals allows us to get good behavior in both a read-heavy or the left plot and a write-heavy or the right plot workload. In this case, we're able to capture our best possible traversal, and the impact of maintaining bundles and bundle dereferences is relatively low in comparison. Whereas for VCAS, for instance, which replaces the bundles or replaces links in the data structure as opposed to augmenting them, pays a cost for every single dereference that it makes. So with all of that kind of laid out, I want to leave with a quick recap of what bundling is and kind of what it provides. The idea is effectively to encode a list of version pointers so that we can provide a traversal through a data structure, a linked data structure, consistent with a particular moment in time. And this allows us to implement range queries that simply follow a single path through the data structure. By augmenting the links, we allow for optimistic traversals. In addition, this technique can be applicable to a variety of data structures, and we're able to retain the fine-grained locking of the original data structure updates while still providing good performance for our range queries, specifically through the optimistic traversals, as I mentioned, and also this incremental approach where we're only visiting those nodes that belong to our snapshot. So kind of the holistic view of this is that bundled references allow us to kind of balance the performance of all of the different ongoing operations and get good overall performance. We also performed some evaluation on a macro benchmark that validated our results in a more realistic workload. And we saw that in that particular case, our technique was able to get better performance than all of our competitors. So with that, I thank you for listening to this talk, and I hope that that some part of it has sparked an idea. I would love to engage and talk more about this and maybe where it can be applied in different settings. And the code is also available if you wish to take a look. So thank you again, and I hope you enjoy our paper.